Okay, let's try the next few questions. So let's try question 43, 44, 45, and 46. Pause the video and do them first.
2,000 years later.
Question 43. The setup is quite similar to the one that we did in the previous video, but this time a bit different is there is friction, and you know the coefficient of friction, and there's 2 kg rest on the table, so this is 2 kg, and this is unknown, and this is what you want to find out with the largest mass that is you can without forcing the block to slide. So think about this. When you try to draw the free-body diagram of the 2 kg that block, you have these forces. So you have weight, which equal to 20 Newton. You have the tension, which the tension actually, if you look into these block here, then you have its weight, which is say let's just assume the answer we want to find is the big M, okay, the so-called maximum mass, okay, so big M G, and then you have the tension. So basically that is all for this block, and so this tension will eventually equal to mg if it is not moving, right? So this mg actually in terms of magnitude should equal to the big mg, and there is also friction as well, and lastly you have the normal force. And since you have the coefficient, so quite likely you can already remind yourself to put down friction equals to mu s end in that case. And when you look at this end, then you can see n should equal to the weight, which is 20 Newton, and so we would have the friction to be 0.6 times the n, which is 20, and so you get the value of friction to be 6 times 2, so 12 Newton. And so looking at this whole block horizontally, if you like to put down horizontally, then you have F equals to T, because the whole thing is not moving, so net force is 0, left force will equal to the right force. So you have 12 equal to tension, which is the big mg, so m would equal to 1.2 kg. Okay, so if it is barely 1 kg, then the whole thing can be staying still. If it is greater than 1.2, then the whole thing will start to slide, and this will go down and this will go to the right. Next question, question 44. This question is easy if you try to draw the diagram. So you have the ground, a flat ground, and you have a suitcase. I'll just draw a box, so it doesn't really matter. And there's a girl trying to lift it up, and the box has a weight of 220 Newton, and then the force pulling it up is actually 140 only. And so they ask you to calculate the reaction force. So here we only have vertical forces, and the pulling force, the weight, and also the normal reaction. So probably something like this. So and since the whole thing doesn't move according to the question, then F equals to 0, and so the upward force, which is the pulling force, plus the normal force should equal to the weight, so 140 plus normal and equal to 220. Very simple calculation, then you'll be able to find the answer as 18 Newton. Next question, question 45. Okay, it said there is a table, there is a block, and the mass is 15, so there is a weight, and let's just take G as 10, so that will be 150 Newton. I skip some step. You can express it by yourself. W equals to mg and etc. On the horizontal table, force 50 Newton is applied vertically down, so it's something like press it down by 50 Newton. So I draw a little bit shorter just to obey the scale, and calculates the force that the block exert onto the table. So I guess the question is quite similar to what we did just now. You want to find a normal force, alright, experienced by the box, and this normal force, according to the Newton's third law, action and reaction pair, will be the same magnitude of the force that is exerted by the box or block to the table. So well, I guess it's really obvious. This would simply be 200 Newton. Okay, so yeah, the answer will be 200. Okay, next question. It's actually quite interesting also, and similar to the example that we did. So here, it has an angle of theta, and you can imagine again, like the example, this angle can be increased. Okay, so it's asking you, so by how much angle then the whole system can stay in equilibrium. Because if you try to increase further, then obviously I guess this is a bigger m, so when you increase further, then these will be able to pull the whole thing down to this. So we are trying to find the equilibrium here. Unfortunately, you don't see any numbers, but then it's actually good for physics because we want to find a more general answer. So let's take a look at the question. It said it is a smooth plane, so you don't have to think about any friction. And let's just try to draw the free body diagram. So like usual, we have the weight, which equals to big mg, and here we have normal reaction. Let's just put R big M to distinguish from, well, actually R is fine because there's no reaction force, and there is a tension that pulling it up, and that is all for the big box. For the small box, we will have again also weight equals to small mg, and this will be tension. Yeah, that is all basically. So from the small box, we can already tell that T should equal to, because the whole thing is in equilibrium, right? Because you may say, is it in equilibrium? Then tension equals to small mg. This is something that we know already. At the same time, if you look at this, the bigger block, then you can say, actually I have no much idea, but I'll just state what we can say. So parallel to the plane, then like usual, I ask you to memorize the component of the weight, right? So we would have the downward force along the plane equals to the one that is going up along the plane. So that will be W sine theta equals to tension, and that actually means W, or let me just express it as big mg, because I don't want to mix up this W and this W, right? So let's just say big mg sine theta equals to the T, which is small mg here. So we will have the G cancel out later on, and I don't think perpendicular will be useful. So perpendicular, I'll just write it out first, just for your reference. Then we will have R equals to big mg cosine theta, but this time is not useful, I believe, because there's no friction. Because if you know friction, then I mean there is friction, then R will be relevant, and then this thing will be relevant. But for now, I don't think it is useful at all. Okay, so then the only thing that we can say about from this expression would simply be sine theta equals to small m over big M. And if you really want to find the angle, then it will simply be small m, well, R sine small m over big M. Yeah, I think that is all you can say about. So again, you can try to think about what if m is much bigger than small m, or what if small m is actually much bigger than the big M, or what if small m actually equal to m. So I'll leave it to you. You can think about different scenario based on what we find here.